A database transaction commits successfully while the subsequent message broker call fails, leaving your local state and external systems out of sync with no automated recovery path available. This dual write problem occurs when you attempt to update a database and notify a message queue independently without the protection of a unified atomic unit of work in your code. Inconsistent states emerge when downstream services never receive critical updates, causing order fulfillment failures or incorrect inventory levels that are nearly impossible to reconcile after the fact without manual intervention. The transactional outbox pattern leverages the atomicity, consistency, isolation, and durability properties of Postgres to ensure that data changes and message events are treated as a single, inseparable operation. You must create a dedicated table named Outbox within your primary database schema to act as a persistent buffer for all outbound events generated by your business logic during transactions. Every Outbox entry requires a unique identifier, which serves as the foundation for message deduplication and tracking throughout the entire lifecycle of the event, from generation to consumption. Store the event data in a JSON binary column type to maintain flexibility for evolving message schemas while allowing Postgres to efficiently index specific fields within the event body if needed. Include metadata columns for the event type, the target destination, and a creation timestamp to allow the relay process to filter and order messages correctly during the distribution phase. When your application processes a business command, it initiates a single database transaction that encompasses both the primary data modification and the insertion of a record into the Outbox table. By committing these two operations together, the database ensures that if the business record persists, the event is also saved, and if the event cannot be saved, the entire business change rolls back.
The Outbox table is merely a storage mechanism, so you need a separate asynchronous relay process to read these entries and forward them to your external message broker, like Kafka or RabbitMQ. The polling publisher is the simplest implementation, where a background worker periodically queries the Outbox table for records that have not yet been marked as processed or delivered to the destination. Frequent polling can introduce significant latency or unnecessary load on the database engine, especially as the volume of events grows and the number of processed records in the table increases over time. To scale your relay process, use the structured query language clause select for update skip locked, which allows multiple workers to fetch distinct batches of messages without blocking each other or causing deadlocks. Create a partial index on the Outbox table that only includes rows where the status is pending to ensure that the polling query remains fast regardless of the total table size. Change data capture is a more advanced approach that tails the Postgres write-ahead lock to detect and stream changes from the Outbox table in near real time without active polling overhead. The write-ahead log is the internal journal where Postgres records every change before applying it to the data files, making it the ultimate source of truth for all committed transactions. Logical decoding allows you to extract these low-level changes and convert them into a structured format that external applications can consume through a standard database connection using a logical replication slot. The PG Output plugin is the standard logical decoding output plugin for Postgres versions 10 and higher, designed specifically to support high-performance streaming of table changes to replication consumers. Debezium is a popular open-source tool that automates the entire change data capture process by monitoring the Outbox table and automatically pushing every new row into a Kafka topic for consumption. Using log tailing reduces the latency between a database commit and message delivery to milliseconds, while removing the need for frequent index scans that characterize the polling publisher method. Regardless of the relay method, you must design for at least once delivery, because network failures or relay crashes can result in the same message being sent to the broker multiple times. Because duplicates are inevitable, the downstream consumers must be idempotent, meaning they can process the same message repeatedly without changing the result beyond the initial application of the event logic. Use the unique Outbox identifier as an idempotency key, which the consumer stores in its own database to check if a specific message has already been handled before starting any new work. Preserving the order of events is critical for business logic consistency, so you must ensure that events for the same aggregate are processed in the sequence they were generated in the database. When using Kafka, map your business aggregate identifier to the message partition key to ensure that all events for a specific entity always land in the same partition and stay ordered. In high-volume systems, the Outbox table can become a bottleneck due to disk contention, so consider using table partitioning in Postgres to split the data across multiple physical storage segments. Partitioning the Outbox table by time allows you to manage large volumes of data efficiently while providing a clean mechanism for deleting old events that are no longer needed by the relay.
Processed rows must be removed regularly to prevent the table from growing indefinitely and slowing down database operations, so implement a background job to truncate or delete old partitions every day. If you use change data capture, you must monitor the lag of your replication slots because a stalled consumer can cause Postgres to retain write-ahead logs until the disk partition is completely full. The relay process must handle broker outages gracefully by retrying with exponential backoff and ensuring that it does not acknowledge or delete Outbox records until the broker confirms successful message receipt. Track the time difference between the Outbox creation timestamp and the moment the message is acknowledged by the broker to gain visibility into the real-time health of your integration pipeline. Configure the max replication slots and max wall size parameters in your PostgreSQL configuration file to ensure the system has enough headroom to handle surges in event generation without crashing the server. Consumers should also prune their idempotency tracking tables periodically to avoid excessive storage costs while maintaining a long enough history to cover the maximum possible delay in message delivery retries. Implement dead letter queues for messages that fail validation or processing on the consumer side to prevent a single bad event from blocking the entire sequence of events in a partition. The Outbox pattern effectively decouples your business microservices from the availability of infrastructure components, allowing your application to remain functional and consistent even when your message broker is completely offline. Verify your implementation by writing integration tests that intentionally fail the message broker connection to confirm that your database transactions still commit and the events remain safely in the Outbox. By centralizing event persistence in the database, you simplify the developer experience as they only need to understand standard database transactions rather than complex distributed state management or external retry logic. When changing event structures, include a version field in your Outbox payload so that the relay and consumers can handle multiple versions of the same event type during a rolling deployment phase. Enterprise systems require this level of rigor to prevent data loss and maintain the integrity of business processes across distributed boundaries, which is why the Outbox pattern is a foundational integration method. As an alternative to application-level logic, you can use database triggers to automatically populate the Outbox table whenever a specific business table is updated, ensuring no event is ever forgotten by developers. However, database triggers can hide business logic and make debugging more difficult, so many teams prefer explicit insertions within the application service layer to maintain clarity and control over event contents. Postgres limits the number of active replication slots by default, so ensure your configuration accommodates all your change data capture workers to avoid errors when starting new relay instances in your cluster. To prevent Outbox writes from impacting your main transaction throughput, ensure that your Outbox table indexes are minimal and that your disk hardware can handle the increased write-ahead log write volume. Optimize your relay process by batching multiple Outbox records into a single message broker request, which significantly increases throughput by reducing the network round-trip overhead for every individual event delivered. When using managed Postgres services like Amazon Relational Database Service, you must enable specific parameters to allow logical replication and grant the necessary permissions to the database user running the relay. Compared to two-phase commits, the Outbox pattern is far more scalable and resilient because it does not require synchronous coordination between different resources, which often leads to system-wide performance degradation. Ensure the relay user has read-only access to the Outbox table and that sensitive information in the event payload is encrypted if your broker is shared across multiple security domains or teams. By following these detailed implementation steps, you transform your Postgres database into a reliable event source that guarantees delivery and maintains system integrity even under the most demanding enterprise integration conditions. This pattern remains the gold standard for microservices communication in 2026 and beyond, providing the stability needed to build complex event-driven architectures that stand the test of time.